So hello everyone, thanks for coming. So I'm gonna talk about XProf, small profiling library, which might not solve all your performance problems, but might come handy in some situations nevertheless. So a few words about me. I'm using Erlang since 10 years now, and I'm still loving it. Currently working at Upliscale. We are a specialized software consultancy company with experience in large-scale soft real-time or low latency systems. The team has many years of experience building such systems, both in Erlang and also Java and C++. The other focus is DevOps and cloud engineering. We have several AWS certified experts in the team. And by the way, if you are interested, want to work with us, or then visit our website or just talk to me directly. It's a bit strange. Let's wait a few seconds if it gets right. Anyway, so the agenda, I will talk about introduce XProf and all its features with a lot of examples. Then a few real-world use cases follow, and then in the end, I will talk a bit about the architecture and its overhead. So, what is profiling according to Wikipedia, which is the ultimate source of truth? Profiling is a form of dynamic program analysis that measures, for example, the space and time complexity of the program, the usage of particular instructions, or the frequency and duration of function calls. Most commonly, profiling information serves to aid program optimization. And what is XProf then? It's an open source, production safe, real time visual profiler for Erlang and Elixir. Elixir is a first class system as well, no drawbacks using it, no limitations, just the same works as well as Erlang. And so XProf is something like a single function profiling. So it does not aim to, or well, you can use that as well, but the main focus is not to compare the average performance of different functions, but to compare different calls to the same function, because it can depend on the input or other circumstances. The tool was created 2 years ago by Michal Niec, and now the team also consists of Pavel Pikula, Wojciech Gawronski, and myself. So the motivation to create this tool 2 years ago is that we had like performance degradation in our live system that we were working on that time. Everything was slower. We didn't know what to do. We were running around in the corridor in panic. We had a few metrics in place, like measuring certain parts of the request handling, but they were too high level, so it was not enough. Adding more metrics to random places, we might put it to wrong place, and it requires like compile time, like deploying the whole system again. It takes a week or something. So we needed like ad hoc measurement and measuring anything what we want, any function, without any instrumentation. Or so the other thing is FProf that we looked at to profile, and many features of XProf. I'm sure I will mix up these two names. Is like we are trying to address certain shortcomings of FProf. For example, FProf traces all the functions in the system, and this gives a lot of overhead. So in a live system, which is already loaded, it was for us at least basically impossible to use FProf. And also the information it provides call count and some of the duration of the functions, but we needed more details like a distribution of the function durations. Also, in particular cases, it's good to have like see the arguments and return values of actual function calls. And then FProf also has this well, kind of hard to digest output a huge Erlang term which you can analyze for minutes, but it's better to have like an intuitive visual feedback immediately and a real-time feedback, so you get it constantly and don't measure for a period of time and then analyze. And there's an extra, XProf also supports shared sessions. So if you open, two people open the browser XProf UI, they will see the same thing. So we can do like a debugging session with my colleague 1,000 miles away, and we can see the same graphs. So I already compared a bit XProf to FProf, but in general, so profiling tools, they are more like this, profiling the whole system, profiling all the functions, and they compare the different functions, but which one is the slow, and this gives too much overhead. So XProf only measures one or a few functions, so it has much less overhead, and it is okay to use in a live system as well. Also, it has this visual representation. Of course, eFlame also has a nice visual representation, but it also provides it offline, like after the measurement. The other class of tools is these tracing tools like Redbug, Recon, Tap, Xrun, just to name a few. They are product safe, so they have overload protection. They just take a number of samples and then they stop. They also have time limit, but they serve a different purpose. You look at each event in detail. You see the arguments, but you don't see the big picture. If you have hundreds of function calls, then it's good to see just the statistics and not just the text lines, so to say. And the third group is like big O&M softwares or monitoring systems like UpSignal, Wombat. What they do is at least for UpSignal, you can instrument your code to measure any function, but that's like a compile time dependency. You need to think about it in advance. And then you monitor those given set of metrics. You monitor it all the time, day and night. You have historic data, as opposed to XProf, where it's ad hoc. You don't have the data, just the real-time one, just for 1 minute, so to say, but you can select any function. You don't need any preparation like deployment, changing your software. So it's really flexible in this way. So how to use XProf or how it looks like? Well, you start the application. Usually it's not running to be safe. So you start from a clear state. When you want to inspect your system, you start up the web UI. You see like a function browser, a text. I can put it here. Okay, seems to work now. So in the text box, it has autocomplete. So you start. I want to profile my try me application. So I try to start to type try me. The T, it first lists all the modules that match the prefix. Then when we have a complete module, then it lists also the exported and the private or local functions. Then I want to profile first the nap function because I think that kind of takes too long for some reason. So when we start measuring, we are seeing like this nice graph. This is like a moving window of the last 1 minute. On the was that right hand side for you? We see the call count, so that's the green line. So this nap function is called about 200 times. Well, probably exactly 200 times per second. And on the other side, you can see the durations here in milliseconds. So the minimum, maximum, percentile values. The average is something like 60 milliseconds, but we can see very high durations as well, like above 100, 160 milliseconds. So to see in what case does this function take so long, there is another feature that we can turn on for each measure function individually. So below each graph, we can see a form, something like this. So we can capture the long calls to this function. So we can set a threshold, 120 milliseconds. If the function call takes longer than that, we want to take 3 samples of that call. So here we can see the captured results, how long it took. It took like 132 milliseconds, the process ID, and then the arguments and the return value. And from the arguments, here we can like get some impression that that's suspicious that the first argument is the long atom. So maybe this function call takes long when the first argument is long, and then the second argument is kind of similar to the duration. So we can infer something, and then we can like narrow down the measurement. So we can, for example, measure the function call when the first argument is not long. I don't have a screenshot for that, but this is kind of the workflow. And then, of course, it has overload protection. So if XProf is overwhelmed with all the trace messages, there's a message queue limit, by default 1000 messages. Then it just stops all tracing in the system. And then it waits for you to like do some modifications. Maybe you were tracing some too expensive function, or the system, the whole system got a bit of pressure, so you can wait until the system is settled, and then with that big orange button you can restart tracing again, and then it continues to measure the functions that remain. So as you have guessed already, XProf uses Erlang tracing in the background. So just a bit of recap about how tracing works in Erlang. There are 2 parts. You can define which processes to trace and which functions to trace. For processes, you can trace on one particular process, all the processes, only the existing processing or processes, or only the new processes which does not exist yet. And on functions, you can specify module functionality, or you can define module function and linearity, or all the functions in a module. And additionally, you can narrow this down with something called match specifications. And then if both process and function filters match, then the intersection it gets traced actually. So how it maps to XProf. XProf has some limitations here, so it only supports tracing on all the processes or none. So that green button is a big on-off switch. And that's how we can like pause tracing and resume. And then of course the text box, it represents in some way the module functionality and the match specs. So there's a limitation. You cannot measure like all the functions in the module, so wildcards are not supported. But actually it's not really what you want anyway. So XProf is like a white box profiling tool. So you know in advance, you know the code, maybe it has it in front of you. So you exactly know which function you want to measure, and you don't want to just randomly start to measure any functions. There might be hundreds of functions in a module, and it presents more overhead than you would have thought. So, but how that text box content can look like, it supports something like XProf flavored match specs, because flavors are good. So apart from supporting module function and RET format, it can be module function followed by something, and that something is inspired by Redbug's restricted trace patterns. It serves to narrow down what you are measuring, so not all calls to a particular function, just selected ones, and it has all the power of Erlang match spec terms, but in a different format. And let's see what that format can be. The first example is always Erlang, and the second one is Elixir, just to see if there is any syntax difference, but there isn't really. So the first example, there is just argument. So instead of RET, you can specify something like a function head or match head. So let's measure the ETS lookups only to the data table, or let's measure registry lookups only to the my up registry. Second example is when we also have guards. So only measure TCP connect to port 80 or 443, or measure registry dispatches to either topic 1 or topic 2. Then you can also specify a body, it's similar to a function body, but it's very restricted. You cannot put there real function calls. It's the return value is ignored. It's only executed for its side effects, and the side effects are achieved with these action functions, special functions like message or caller. The message is the most important one. On the Erlang tracing level, what it does, it adds an extra field to the trace message with the content that you specify here. And on the XProf level, if you don't have long call capturing on, it does nothing, no effect. But when you capture actually the arguments, instead of the arguments, this thing will be captured instead, which has the two main use cases. One is to, if you don't care about the arguments, but instead you wonder who called this list subtract function when it took so long. And the other example is when you are interested only a part of the arguments or some derived value from the arguments. So here are two examples for that. And also it's getting complicated that there are also arguments, guard, and body present in these queries. Of course, this is in one line. Just it didn't fit on my slide. So the first example is to insert into ETS table a record data, but we are only interested in one field of that record. And the second example is to measure enum fetch when it is called for a list, and then let's capture the length of the list, not the content of the list. Even further, you can define multiple clauses as well. Well, this is rarely needed, so this is just a contrived example with the same content achieved by guard, so measuring connecting to either of the TCP ports or dispatching to either of the registry topics. And I have one thing to note here, that the body is actually mandatory if you have multiple clauses. So, but you can put there any value because the return value doesn't matter. So you can put there true, false, nil, whatever. Oh, this example will come up later, so I wanted to spend a little time on this. So it would be very nice if we could support string prefix matching, so that only measure emysql execute calls when the query starts with select F1. But unfortunately, that syntax is not yet supported because it needs some trickery. It's a syntactic sugar in the Erlang world. So instead, nowadays, you can put this a bit uglier list matching form where you actually put each character as a number, and that's the head of the list. That's ugly, but can be useful until the support for the nicer version comes out. And then to go even more complicated, there is a bit of sampling implemented with something called the trace control word. Trace control word is a global integer in the VM, which can be read and set both from the match specification and also from the Erlang word. So here, let's see what happens exactly. So if the trace control word value is 9 or above, just reset it and do the default behavior, which is to measure that function call, and otherwise just increment the trace control word and then silence that function call with this message false trick. So basically what happens is you measure only every 10th function call. So if you have too many function calls, like thousands or 10,000, you can restrict that and just take a sample of that. Actually, this looks like a bit complicated, so maybe in the future it would be nice to have some shortcut for this. And of course, there is a lot more. There is a lot of power in match specifications in Erlang, so I strongly advise to read the reference manual for the match specifications. I do it almost every month, and I always find something new and interesting there. And there are some restrictions for this function format for match specs in the documentation of the MS transform, you can find them also with some other examples. Very inspiring. So let's see some real-world use cases. First, the original issue, which I named like the fat requests issue. So as I said, the system performance was degraded for some mysterious reasons. We've seen increased response times, general slowness, and well, just to give a like bit of detail about the system in a very generic way, there were objects requested, and then each object is associated with a few business rules, and then each business rule is associated also with a few objects or some. So it's many relation, and when the request comes in, before it is handled, there is a preparation phase when all the business rules are fetched from memory associated with the requested object. So that's what's happened. What happens, and then this is a screenshot from 2 years ago, the original investigation. So this is measuring that exactly, I guess, that preparation phase. So what we can see on this graph, let's see, there are about 200 or a bit more than 200 requests in the system. It's kind of constant. So you can see on the green line. And then the duration, well, the average is down there, around 50 milliseconds. Actually, the median and the normal values are even lower, because this should take really just like a few milliseconds just to fetch from memory, read from ETS tables. But actually there are, yeah, the color is a bit stained, but actually I think you can see that there are a lot of outliers here, which take actually more than 300 or 400 milliseconds. So that's extreme. So now the other nice feature of XProf comes in to capture some of the long codes to see what are the arguments and return values. Unfortunately, that screenshot is not available, but what we've seen is that, of course, the return value of this function is all the data that is fetched, and what we see that there are objects which are associated with like hundreds of business rules, which we didn't really anticipate. I saw that there are like people clicking it together, and it could be like 10 business rules maximum. And also there were business rules associated with hundreds of objects. So in the end, that pool function call was fetching tens of megabytes of data. And of course, it took like several hundreds of milliseconds just to prepare that request handling before the request could actually be handled and real business logic could take place. So XProf was really useful in 2 ways in this case. One is to show actual examples of these fat objects. So we could like present it and prove it that, hey, you've configured such objects in there. And also on the previous graph, we've seen that this case happens actually quite frequently. So it's not just once in an hour, but actually it's every second. And it cripples the system. So after we did not knowledge, actually we could go to the technical management and say that, okay, we need time to address this because this is serious. And also we had a clue where the problem is. Then after that, it was easy to change the representation and use a more efficient structure. The other examples are more recent and not that serious, so to say. So the first one is in our monitoring system, we've seen that the maximum latency response time was sometimes like spiking to 5 seconds. Otherwise, it was normal, but there were periods in this, it takes 1 hour that there are extreme cases. And actually, this repeated like every 2 hours. Very strange. So when I dig deeper, I found that actually some of the requests, just a few of them, so low percentage, was initiating a MySQL query. And then I was measuring that function which does the MySQL queries. As you can see, it's quite only just a few of them, so not even once a second, but we can see the pattern when it happens, and then we can also see that they all last for 5 seconds. That's already very suspicious. And of course, with capturing some of the examples, we can see that they all return with the same error, which is connection lock timeout, which means that digging into the code, it turns out that actually the request was waiting for a free connection on the Erlang level, so it couldn't even send out the request on the wire, and it timed out after 5 seconds. Poor function. So after I increase the pool size in the middle, then, well, I don't know if you can see the yellow lines, they disappear, so the response time goes down to normal values. So in this case, you could also use normal tracing, because actually all the function calls were actually problematic, but still the pattern is, I think it's more intuitive to see it on a graphical way. The last example is an issue of message queue buildup, when we've seen on our monitoring system that in certain periods it's pretty much going up, and it turned out that there is well, quite easily, because as you see, the maximum is 1,000 messages. We know that there is a bottleneck server in the system which has a message queue limit, and that server, I just observed that it freezes for some time. Reduction count didn't increase. It doesn't do anything, and then meanwhile it receives a lot of messages and cannot handle them. So let's observe it with XProf. So the first graph is actually gen server handle cost, because it receives most of its requests with this function. So measuring how much it takes. Here is normal operation. Usually there are 5-6 requests per second, and the time it takes to handle it is quite low. And then we've seen there silent periods when actually nothing happened. Actually, what happens is there is one request that takes 30 seconds to complete, huge number. And then after that, it can handle a few messages again, but then this freeze happens again. So we can see the pattern that it happens. It's not just one big freeze, it's a lot of freezes, so to say. And this function also does MySQL queries, so I was measuring also the actual query duration. So now on the wire, so when it has the free connection, yeah. And the same pattern appears, so it's mostly write operations. So I also captured the long calls, few samples of them. So one thing to note is that call time is actually 50 seconds here, so not 30 seconds, even longer than it appears. So is this a bug in XProf? Well, not really. There is a limitation, HDR histogram, which is used in the background. It uses a predefined interval to store the duration. So it has a maximum value, which is configurable in XProf, but it's by default 30 seconds. So every call that takes longer will be just stored at 30 seconds. But this is actually okay, because any function which takes longer than a few seconds is just like infinity. So you just see a big spike. It doesn't really matter how long it takes. It's wrong anyway, in general. But if you capture actually the long calls, you can see the precise values for the duration. The other thing that you can see that they again return with the same error. I mean, all the calls, all the long calls, it's like lock wait timeout exceeded. So this time it's a lock in the MySQL DB. So these queries actually couldn't really finish successfully. And after I waited like half an hour, the last call that I captured, it took actually 49 seconds. So it actually just finished on time before the lock timed out. So lucky guy, and it returned with some okay result. And then the green line resumes again, so we can see that the gen server again serves normally 5, 6, 7 requests. And from here, of course, it's like a usage issue, how we use the MySQL DBs, how we initiate the queries and locks and things like that. But as a starter, XProf was very useful to see the patterns in the graph. So just to sum up this XProf workflow, how it looks like. So initially you start from some suspicious graph on the monitoring system or some triggers alerts. Then XProf to the help, you start it up for some ad hoc debugging, and then in the end you can use some other tools to debug or modify code and then profit. And the details of the XProf workflow. So usually you go from an outer function and go deeper to the called functions. You can also measure like two inner functions parallel to each other. So you can compare them, which one is slower, which one is the bad guy. You can do it iteratively and then capture arguments for the long function so that you see or you can guess what the problem could be. You can also use match specifications to narrow down the measurements. So you only measure the bad, so to say, bad function calls, and you go back and repeat this again until you find the particular function call and particular arguments which are programmatic, or the particular return value, maybe an error, which tells you what the problem actually is. So just to look briefly to the architecture, it's very simple. So there is a singleton tracer process. It receives all the trace messages, and then there is a separate handler process for each function, which owns an HDR histogram, each of them, and then it takes a snapshot every second and stores that in ETS table together with the captured arguments. And then the browser, it talks to cowboy REST handler process, and that one reads only from the ETS table, so it doesn't talk to the tracer infrastructure, so it doesn't interrupt that. And a bit about the overhead of XProf. Well, I tried XProf profiling XProf itself. Well, you can do that on the web server part. It looks like this. This is what I call a healthy function, so the minimum and maximum are quite close. There's nothing much to see here. To profile the other parts, it's a bit harder because there is a limitation in Erlang that one process cannot trace itself. So we need to use another process to trace XProf itself. So I chose to use fprofx, which is quite similar. Well, the output is kind of hard to digest, so I tried to use this crash kind output. But here, so profiling XProf only gives the information which part of XProf is the slowest. It actually found one application getem call which is unnecessary, but otherwise actually doesn't tell what the impact of XProf is on the whole system. And actually the impact is mostly the overhead of tracing itself, because it affects all the processes. The overhead of message sending and then copying terms. If there are large arguments or large return values, they have to be copies from the tracee to the tracer process. So that's the actual overhead, and XProf tries to do what it can to reduce the overhead of that, but it's also the responsibility of the user to carefully select functions which are less expensive to measure. And then there are a lot of future ideas in the two fields, the usability and new features, and the overhead part to reduce overhead. New features is to improve visualization, add heap map, overlay some events like crashed functions or too long functions, add shortcuts for complex math specifications or maybe just buttons, and also to represent other trace events like garbage collection or scheduling related ones. And on the overhead part, we can introduce sampling both on the process level, so just measure selected processes, or on the event level, as the previous example showed, like only measure selected function calls. And, in OTP 19, apart from the whole tracing infrastructure being optimized a lot, also something called tracer module NIFs were introduced, where you can actually replace the default message sending tracing implementation with your own NIF. And I'm very excited about that. It opens up a whole new world of tracing to add some XProf specific action there, and this could hopefully reduce the overhead of message passing. And there are other ideas to use not the internal Erlang tracing, but LTTNG or other rim trace mechanisms, and then consume the output stream of those tools. And of course, if you have any more ideas, please tell us. We are open to all of them. And yeah, so just to sum up, XProf is a simple ad hoc profiling tool. It's also, you can consider it an enhanced tracing tool with immediate visual feedback and very intuitive feedback. And it has various use cases, so it's available as a hex package, and also the source is up on GitHub. So please try it and give feedback, tell us your ideas, and contribute if you like. So thank you. Don't know if we have time for any questions.
We've got about 4 minutes until the next talk begins. So if there's
Okay.
like really quick questions, anyone's got anything?
Yeah, well, you can download the hex package. You can, I guess, you can go to the GitHub page, and there is a bit of README, and you can see the instructions. You need to include it as a rebar dependency in your release, and then you can just start it up and fire up the UI, and that's it. And then click around. Thanks for the question. Okay. Okay. Thank you for listening.